Here we go.
Okay, we're recording.
Okay, so welcome to HAO Colloquium, everyone. Our today's speaker is Craig DeForest. Craig DeForest got his start in studying plasma physics in the mid-1980s, working at the D3D tokamak facility in San Diego. Rumors that he was bit by a radioactive lizard there and now fights crime by night are greatly exaggerated. He holds a 1989 bachelor's degree from Reed College and a 1995 doctorate from Stanford University. And over the past 25 years has made a career of developing novel instrumentation and analysis techniques. He chairs the AASSPT and leads the Punch mission. He is here today to talk about some of the techniques used by Punch to merge data from 4 separate cameras into polarimetric background subtracted data products. The title of his talk today is Polarimetry and PSFs Behind the Scenes with Punch Data Analysis. Right?
Thank you, Monkey. Hi, I'm pretty thrilled that so many people turned out in the snow, right? So let's see. Here's a quick outline of where we're going to go. I'm going to give everyone an overview reminder of what Punch is all about and tell you about our status. I'll talk a little bit about PSFs and PSF correction, which is something that we're very excited about, but doesn't bear an entire hour-long or microcentury-long seminar. And then I'll talk about linear polarimetry, which is doing that here at HAO is sort of like bringing coal to Newcastle, but on the other hand, it bears talking about. So I'll discuss some points that came up in the course of developing the Punch formalism to get the pipeline working. Let's see, so the status. There we go. All right, I think many of you have seen a slide like this before. We're trying to understand how the corona gives rise to the heliosphere and to the solar wind. And so we're imaging the outer portion of the corona and the inner portion of the heliosphere as seamlessly as possible to see them as a unified system. We're trying to do direct continuous 3D imaging of that entire inner solar system over a 90-degree wide field of view. I'd like to point out, Punch is not a telescope, right? It's a wide field camera. We're seeing things that are about to sweep over the Earth in perspective. We'll do 3D imaging using polarimetry, which I'll talk about later in the talk. The structure of the mission is we have 4 small satellites that are all going to a 620-kilometer sun-synchronous polar orbit, everybody's favorite orbit. We have a 2-year mission that launches in April of 25. I just came from our rideshare missions pre-launch working group meeting, and they're claiming February of 25, but don't you believe it. So we're in phase C, final design and fabrication. Our next milestone is system integration review in May, maybe in June, we'll see. And that's our transition to phase D, which is integration. So we're pretty well along. All right, this is our science. I'm not going to go over every single.
Where it's going to be built.
Sorry?
Where is it built?
Where is Punch being built? Southwest Research, San Antonio.
Okay.
So we're building the spacecraft and the whole kit and caboodle. The coronagraph is being built at the Naval Research Laboratory. The cameras came from Rutherford. So these are the various topics. They ramify into 2 major objectives, one of which is to understand the ambient solar wind, and that's this global evolving wind flow, the Alpine zone, and microstructures and turbulence. The other one of which is the big, bright, shiny things that make space weather, CME, trajectory, shock dynamics, and co-rotating interaction region formation. Some of you have seen this movie before, at least once. This is the Sun to Earth movie that we made with stereo, showing the CME from I guess 2008, crossing the various fields of view, sweeping over Venus and impacting the Earth, and directly connecting by tracking this event. The features down here in the EUV corona all the way out to the in situ measurements that were being made by the wind spacecraft at the time. So there we go. As it sweeps over, you can see the wind density gauge peg. Wham. There it is. Okay, so this is the punch field of view from the outer corona through the inner heliosphere, and we're imaging that as seamlessly as possible. You have to have a scene, but we're doing our best to minimize it. These are the different observatories that we have. We have one of the one on the left, which is a coronagraph called Narrow Field Imager, or NIFI, and three of the one on the right, which is a Wide Field Imager, or WIFI, that's being built at Southwest San Antonio right now. The spacecraft themselves that carry the instruments are interchangeable, and you can see they're about 1 meter long, so it's not very long. Let's see, whoops, wrong button. There we go. So how do these things work, and why are there four? Well, these are the fields of view on the sky as they orbit. They spread out around the Earth to make a trefoil field of view in space. The reason there are four of them is when we decided we had to be close to the ground stations to get the data back, we discovered there was a giant planet in the way. So we had to spread out the instruments until they were around the planet. So as the constellation orbits, this trefoil rotates on the sky, and we combine the exposures to cover the entire 90-degree wide field of view every 30 minutes or so. Over here on the right, you can see a rendering of the spacecraft going around. I mentioned we do polarimetry. We also do extremely precise photometry. I don't expect you to read this eye chart. This is a diagram showing the steps in our ground pipeline to merge the data from these instruments into seamless data products. What we're going to focus on today is first was three features. The first of them is something that is very commonly done here at HAO, but is not commonly done in space, which is we use a proper quartic photometric flat fielding, so that we fit a quartic response function to every single pixel. That allows us to remove nonlinearities in the detector and get our photometry nailed down. The second one, which I will talk about, is PSF correction. We're merging data from multiple cameras into one mosaic. And so we need to match the point spread function of those telescopes one to the other, otherwise the mosaic will have a seam. So we've developed a formalism to do that. And then most of at least the second half of this seminar will be on resolving polarization. We're taking polarization signals from each camera at different angles and merging them into a single unified whole in PB. And that required just a little bit of care in thinking through the analysis. So here are some pictures, everybody likes pictures. This is our wide field imager engineering model when it was going in for stray light testing. So you can see there's it's hard to point on Google Meet right here. If you can see it on the left, that little tiny tube is where the optics are. There's a Rutherford camera in the back here. In the front, we've got very deep baffling that attenuates sunlight by an estimated 16 orders of magnitude. So it doesn't suck. Over on the right is an image taken inside NRL's vacuum facility for stray light measurement. And we actually couldn't detect the amount of stray light directly, so we had to use a double scatter approach. This little bright region here is mostly the back of the chamber, but right where I've drawn this rectangle is where we expect Fresnel scattered light from the incoming beam to come around the detector. With the scattering in the chamber plus the Fresnel scattering, we still had a measured amplitude less than 10 counts compared to a requirement of 1200. So we're doing just fine, 16 orders of magnitude. This is the entire engineering model observatory, all integrated and placed in EMI testing. It's been through a full test regimen by thermal back and all that. This is the engineering model observatory. This is all from about 6 months ago in an integration frame in our clean room. That's a giant clean room down in San Antonio, or I guess it's a room that's clean. We've migrated them all to an actual certified clean room. This is the flight model wide field imager taken just about a week ago. This is the first of 3. It's been assembled and is undergoing test right now. They just vibrated over the weekend, and they're scheduled to go into thermal back later this week. Although we did not go to heroic measures to darken the baffles, we did use some space qualified dark coatings. And so that is darker than most dark things in, say, this room, but it's hard to tell on an image. So where are we? We are in phase CD. We combine those two phases, but really phase C of the standard NASA rubric, which is final design and fabrication. We've put together a complete flight model WIFI, and of course we're still assembling the NIFI. Spacecraft, we've got most of our parts in hand, and the subsystems are largely integrated, but we're still getting ready for full integration after system integration review. And on the ground, we're developing the SOC. We're working very hard to do something that's unusual in the space industry, which is have the SOC ready to go when we launch, so that we'll start getting data when we can. Launches, we're anticipating April of 25. Next science team meeting, which you should come to, is right here on July 6 and 7. And the inimitable Sarah Gibson is organizing that. Of course, the announcements and so forth will be up on the website. So come to that, please.
Where's the SOC?
The SOC is in Southwest Research Boulder, so right
Okay.
across town. But of course, the data are available everywhere. All right, PSF regularization. So here's the problem in a nutshell, right? We have these fields of view that we have to merge. And the images here are representative. They're taken from stereo, from one of the stereo roll campaigns. So we mocked those up to have the same optical distortion and so forth that Punch will have, and then redistorted them into our final data product coordinate system, which is azimuthal equidistant projection of the celestial sphere. We have a large enough field of view, we have to care about that. So radius on this image on the left or on the right is proportional to elongation from the sun. Elongation being the apparent distance, the angle from the sun. So distance on that plane is proportional to the actual angle. And then the azimuth is the azimuth, as you will be aware of the sun. The problem that we have here, of course, is when we merge these things, I mentioned it before. Let's see if I can find my cursor. Can't, but that's all right. On the left, you can see those overlapping regions. They're from different parts of the field of view of each instrument. And so the various optical aberrations will be pointing in different directions. So we need to be able to solve that problem.
What is the spin period?
These go around once every 100 minutes or so. And they're 3-axis stabilized. So while we're exposing, we're locked onto the celestial coordinate system. Interestingly, Punch doesn't know where the sun is. We have sun sensors for emergencies, but we normally point relative to the star field, and we have to keep a solar ephemeris on board so that we know where to point. Regularizing images. So we dove into this, and it turns out this has been a problem for some time. As you can see, this is the cover page for Dioptrice, which was published by Kepler, Galilei, and Peña in 1611. That was the first citation we could find of problems with coma in telescopes. And so we're trying to fix this problem that's been around since then. Over on the left, we have the far left frame there is some modeled point spread function images. We have a model star field that happens to be a square grid. And over on the right is after we've corrected it. So we think we can do this. So how does this work? Well, the way you make a point spread function is you have a convolution kernel that has to be slowly varying across your field of view. So in any neighborhood in the image, the point spread effects are convolved on top of the image. So we make use of the convolution theorem that transfers convolution in real space to multiplication in Fourier space, right? Pretty straightforward. So you start with an image convolved with a kernel, that's the top line there, and you take the inverse Fourier transform of the Fourier transforms of the two things. That's how you get the convolution. Well, you can invert that pretty straightforwardly by dividing by the Fourier transform of the kernel. So in this case, rather than saying f of k, I've made a curly k. So the middle term there is just the initial image after convolution. You divide it by the Fourier transform of the kernel, you're done. The problem is, of course, you can't divide by 0. So if any of the Fourier components are 0, you try to divide them, the whole thing blows up. So you have to use a regularized reciprocal. That's that Gothic R that kind of rolls over and gives you a better approximation. But this theory is pretty well understood. I just haven't seen it applied to telescopes before. Usually when you do deconvolution, you're trying to deconvolve to get the sharpest image you can. But for punch, we're not trying to do that. We're trying to get the most uniform image we can. So that means that we can use straightforward deconvolution, but it's everywhere we would be dividing by a small number, we have to also multiply times a small number. So we can produce what I call a transfer PSF. It has the property that if you convolve it with some arbitrary PSF image, it will transfer it to have the PSF you desire. As long as you select the PSF you desire, so that all of its Fourier components are small compared to the Fourier components in the original convolved PSF image, right? As long as they're small where the other one is small, then you're okay. So in the top here, here's an example. We have a target PSF that's tall and narrow. We have a real PSF that's spread out sort of like a Lorentzian. So we convolve some image, convolve our image with that. We want to get to the sharper response. Panel B here, top left, second from the left. Those are the Fourier transforms, also known as the modulation transfer functions of the two PSFs. And you'll notice that the one we want is larger, but it's not too much larger than the one we have. So we don't have to divide by a small number to get from one to the other. When we convolve the two MTFs together, the reciprocal of one times the other, we get this transfer PSF here that sort of is sharp. There's a little bit of ringing at the outside. Turns out that doesn't matter very much. When we convolve our original PSF with the transfer, it turns into the PSF we want. Clear as mud, right? So we have these two different point spread functions. We have the one we want. We have the one we have. We develop a transfer PSF that allows us to convert from one to the other. As long as the properties of the destination PSF are correct, everything works. We don't get ringing and noise and so forth. Down below is an example of if it doesn't work. If we get too ambitious, we have data that are really blurred, this really wide PSF. There's too much, the ratio between these is too much. And so when we go to try and make a transfer PSF, it comes out wonky, and we don't get the correction we want. So this is just pointing out that you have to actually, you can't get too ambitious. Here's how it works. So we had some starfield data lying around, as one does. This was taken through a f/2.8 Nikon wide field lens some years ago from my rooftop. You can see some sample stars over here on the left, illustrating the point spread function of that lens very well. And it's different in different parts of the field of view. These are 9 different subregions that are just regularly sampled across a large image. Over on the right, this is after correction. You can see that all the stars have essentially the same shape. This was an early image, and you can see we were a little too ambitious here. There were a couple of Fourier components that rang in the upper right and the upper center fields of view. That's those little stripes around the star. But by and large, it worked very well. And you can see that all the stars have exactly the same shape, aside from those occasional artifacts. So pretty happy about that. We applied that to Wi-Fi images. So we took Wi-Fi out. This is the engineering model, the one I showed you pictures of, integrated on the spacecraft. Instead of integrating on the spacecraft, we integrated it on a pickup truck and carried it to McDonald Observatory down in South Texas. Took some starfield images with it. That was a lot of fun. The individual images are pretty noisy, but when we merge together into co-adding of stars, you can see very clearly that it has a lot of coma. That's to be expected. It's a really wide field optical system in a compact lens capsule, so it's going to have coma. This is our first cut at correcting. We try to detect what the PSF is on the left and correct it on the right. You can see we had some issues. There's still some residual noise, particularly in the edges of the field where there weren't as many stars as near the center, and that left some residual tails here. But by and large, we were able to correct despite the noise issues. So once we run this on some lower noise data through the same instrument, we anticipate that we'll be able to fully correct. I should also point out, if you look at the brightness scale here in the middle, we've greatly exaggerated the faint stuff. So this tail here is like 1% of the core. So it's not much.
So that's a logarithmic scale.
Correct.
Yeah.
We're trying to show off all the flaws. So
Sure.
Yeah.
Sounds-
So anyway, that is what we're doing. That is our PSF correction step. As you can see, it was still in process when I made this slide about a month ago. But Marcus Hughes has been working on this, and he's been doing a great job of it. So when we merge the punch data, unless you go back to the level 0 and do your own processing, what you will get is not the very highest resolution we can produce. What you'll get is the most uniform resolution we can produce across the entire thing. Let's see. So why is this not advancing? Here we go. So I'll pause here for a moment. We can all stop, ponder PSFs. I'll take any questions we have, or we'll just keep moving on into linear polarimetry. Star of the show.
So that mosaic image that you just showed,
Yeah.
the center image in the corrected side, on the right side, it's a little bit wider than the uncorrected one. Is this
Yep.
showing how your PSF is maybe not as
Exactly.
delta, but it does show uniformity across the field of view? Is that what you're saying?
Exactly. So we're optimizing not to get the highest resolution at the center, but rather to get the most uniformity.
Yeah.
And so that's exactly right. So from the standpoint of the algorithm, a delta function is aberrated, right? Because it's not the uniform thing anywhere. Yeah.
So what's the next step with improving that? I mean, I would imagine you get some more different kinds of data, and you play around with your function, your algorithm, and you optimize it a bunch more.
So there are a couple of things we can tweak. One is how hard the rollover is in the reciprocal function.
Yeah.
Another, and that trades noise versus accuracy.
Yeah.
We can tune the size of the final PSF, and we can adjust our PSF detection algorithm. For these data, the comas that you see around the outside, the residuals, are largely an effect of noise interfering with our ability to measure the PSF out there. We just had a really noisy data set. So we tried to beat it down by averaging over a bunch of stars, but there's a limit to how much you can do.
So you could also fold in some physics or some knowledge or some, assumptions
Right.
into that that would allow you to tweak it and make it go in the direction you want, which is basically what you're doing. Is you want to increase your signal to noise, right?
Right.
And you know exactly what signal you're looking for.
Mhm.
And you can say, oh, but wait a minute, you're presupposing what your science is. Of course, everyone presupposes what their science is. You just keep iterating to see, when you twist the knobs, what are you most sensitive to get the product you want.
Exactly. So in this case, we're very fortunate because we have a star field. The star field is very well characterized.
Yeah.
So we know what we're aiming for.
Right.
Right.
Yeah.
And once we got that site in, we know that's a calibration for the coronal data, which is what we really want.
Right, except coronal data is not a star field, and characteristics of the coronal data is a little different, right? But you may say, well, optics are optics are optics, and it doesn't really matter if I get the star field right. I know I've got my corona correct.
That's where I'm going.
Yeah, I'm trying to think if there may be pitfalls in that.
It's like photographing an Air Force test target, except it's on the celestial sphere.
Yeah. Yeah, I'm just wondering if there may be something associated with distributed images of a distributed signal or
Mhm.
target or whatever it is you want to call it, basically the corona, how that might be different. Your image processing might be different than when you're looking at dots.
Absolutely. In fact, let's revisit that in just a moment, because that presage is something I'm about to show. All right.
Just to segue, one question,
yes.
if I may. So just to segue on that in terms of folding in physics knowledge, would you, even if you had a noisy field here, would you be able to use the transfer PSF from, say, the top left for the bottom right, expecting that there's some symmetry in how the PSF varies across the field?
Well, that's
And-
it. Go ahead.
Oh, no, that was it. I was just wondering if the corrections or the transfer functions that you applied to get from the left to the right for the subfield that's on the top left, if you could apply the same correction for the subfield on the bottom right and then expect a similar improvement.
Absolutely. Absolutely. That's a good question. So we ought to be able to use the fact that the instrument is circularly symmetric. However, this whole mission is about diving down into and grotting around in the muck of what a normal measurement would be, to the degree that we can't actually rely on the optics being exactly circularly symmetric. So it's a good test, right? You check and see that the opposite sides are approximately symmetric, but I don't think we would actually use that for flight data. The biggest problem with this data set was that we couldn't cool the camera down. The camera's designed to be cooled in space, and so we had to operate it at room temperature, and that meant that the read noise was something like a factor of 1,000 more than it will be in flight, and that was what really made it hard to make this particular measurement.
And so if I'm following right, that means that the noise, wherever you had fewer stars in the subfield, that threw off your estimation of the actual PSF, was it?
Yes, yes. That's our hypothesis for what made the edges more rough cut. And I'm sort of showing that basically in the interest of scientific honesty, right? That this wasn't exactly what we wanted, but we think we understand why it wasn't.
Cool, thank you.
Pleasure. All right, let's move into polarization so we actually get you out of here on time. Many of you may be aware of this, but light can be linearly polarized. So there's an electric field, and if you set the direction of oscillation of the field, you've linearly polarized the light. And we make use of that in all kinds of things. We're using polarization for 3D imaging of the corona. The light that you see in the corona or in the young solar wind is Thomson scattered. So electric field comes in, shakes each electron individually. The electrons then become dipole antennas and re-radiate. It's Thomson scattering in a nutshell. But the electric field is projected by cosine of the scattering angle. And so if you scatter at right angles, the light is fully polarized. The electric field out of the screen in this diagram is not affected. The electric field in the screen is reduced by cosine of 90 degrees, which is 0. So the light that comes out is fully polarized. So the degree of polarization allows us to relate that scattering angle to the location of an object. In the lower left here, you've got the sun, you've got Punch or some arbitrary observer at the Earth, and some object that Punch is looking at. You've got an elongation angle, that's this curly epsilon that tells you where on the sky the object is. We get the scattering angle chi from the degree of polarization, and that allows us to solve this triangle. And that's a straightforward thing. It can be done automatically, and we will be producing data products that do that for you. There is some ambiguity, right? The object could be in front of or behind the Thomson surface there. You have to sort that out, but we can do all the rest for you. Okay, so that means we have to understand what the polarization is specifically. So in the K corona, the polarization from Thomson scattering is tangential, right? The component of the light polarized in a radial direction is attenuated, so the net polarization is perpendicular to that. And especially if you've used any of the MARC data from the top of Mauna Loa, you know BT minus BR is what you're seeing, right? It's the brightness through a tangential polarizer minus that through a radial polarizer. That excess polarized brightness it reflects the density in the corona. All right. So the other half of this is, what are we doing with punch? And I want to just sort of give you a sense of how hard we have to work in the SOC to get you the data products you want. This is some of you, again, have seen this movie before, but it might have been a few years. This is a movie taken with HAO. It's a stereo instrument looking back toward the Earth. It's about 45 degrees ahead of us on our orbit looking back. These vertical stripes here are caused by Venus on the right and Earth on the left. And to the left of the Earth is the occulter that's designed to block the Earth so that doesn't happen. So, you know, nothing works quite right. You can see the star field going by, and the photometric bar here, which I want to draw your attention to, goes from 0 to 30. That's counts per second per pixel for a 2-hour exposure. Okay, so it's a kind of an arbitrary DN kind of count, but it is quantitative and it will be preserved through. So watch that number because it'll shrink. So when we try to reduce these data, the first thing we've got to do is get rid of the zodiacal light. That's that bright glow on the right. So we take the entire data set, we subtract the minimum from each pixel, and you get this. Now there's a lot more stars. That's because we've zoomed in on the photometric range. It's now 0 to 1 instead of 0 to 30. Problem is now the stars are overwhelming the signal. So we resample to fix the stars, and being able to do that properly and photometrically was an advance 12 years ago, but now it's sort of de rigueur. You can see the Earth and Venus moving relative to the star field along with the pieces of the instrument, right? Because you're tracking the stars. Now we do the same trick. We subtract the minimum value of each pixel in that coordinate system, and we have this. So you can see now the residual from the F corona because it wasn't really fixed from the zodiacal light. You can also see some statistical aberrations that take the form of horizontal streaks. That's caused by the star's passage changing the statistics of that pixel. And so it sort of prints through into our residuals. But you can start to see the K corona here. We're now at 0 to 0.1, right? So a factor of 300 inside the original data. We can go farther. We can remove a smoothly varying function from each pixel in time. You get this. That's about as far as you can get on a pixel by pixel basis. But look at the scale now, 0 to 0.03. So we're a factor of 1,000 inside the original data. Then we can Fourier filter. We can look for moving objects, like the solar wind moves. Now this is kind of jumpy on this screen, but it's very smooth on my screen. You can actually see solar wind objects moving by. So that's what we have to do routinely for punch instead of on a one-off basis as we did for stereo. And this is resampled back into solar coordinates. All right. So there's a problem here, which is that with punch, we don't just want brightness, we want polarization. So we have lots of backgrounds, right? Instrumental scattering is likely to be polarized. The F corona is up to 20% polarized. We know this because it's been measured. And then, of course, the star field, just to add insult to injury, the star field is polarized too. And all of these are fixed in different coordinate systems. So not only do we have to resample to fix each of these in order to get that background note, we also have to track the degree of polarization in each of those systems. So how do you do that? Well, it's a problem because, well, here we go. We need to describe our polarization with quasi-scalar values that are additive, just like the brightness is, right? If we use a Stokes parameter, things can have a negative Stokes brightness in any parameter but I. That's a problem for us because we can't subtract that negative value. It'll make things brighter, right? The way all these background measurements work is we find the faintest value. But if it's possible to have background that is non-zero and actually negative, then that technique doesn't work. So we have to represent polarization with these quasi-scalar additive values. So now we're going to dive into my favorite thing for this last year, which is how we describe linear polarization. We're going to go on a little excursion. Many of you have been here before, but it's worth it. The scenery is good. So this is how we all learn to describe linear polarization when we're in elementary school, right? We know the amount of polarization, How much darker does it get through the filter? We know the angle you have to turn the filter to get the null or the brightest value, right? So I, beta, and P, little p being the degree of polarization. Sort of the first, it's a primary school first way of looking at this. But of course, it doesn't have, right, simple direct projection. The drawbacks are it's very difficult to manipulate, and the polarization angle doesn't transform in a simple way when you add signals together, because that little p is sort of it's a relative parameter. So when you combine signals or subtract them, it doesn't change in an obvious way. So we need something better, right? We all learn in graduate school or in college, as the case may be, the Stokes system, right? You have I is your total brightness. You have Q and U are these parameters that we use to describe the plus mode and the cross mode for polarization. And we can measure those directly, and the textbooks do have us measuring directly by actually physically putting polarizers at different angles, right? Take the 4 measurements, bam, you're done. There's this other thing, circular polarization, which you learn later, right? But we're doing linear polarization now. So the benefits, oh, right, a side effect or a side note is the Stokes parameters are fixed in the instrument coordinate system or the lab coordinate system. PB rotates relative to that system. So people often use B and PB, where PB is sort of a Q-like parameter that rotates in the image plane, so that it's always radial. And of course, there's a Stokes complement to PB, which is PB prime, which nobody ever uses because it's 0 in the corona, which is the degree of polarization at 45 degrees to a radial angle. Okay, benefits. You got direct connection to theory, extensive analysis. Everyone's familiar with the Stokes parameters. You know, you can use Mueller matrices and stuff, and everybody likes that. And of course, you can extend that to circular polarization. The problem is, for punch, right, that Q and U are signed. And of course, from an aesthetic point of view, I is a special parameter. It's different than the other two. And so you're not describing this in a uniform and symmetric way that matches the uniform and symmetric system you're describing. So yes, Stokes is great. I'm not trying to run down the work, Stokes vectors or even Jones vectors, just to say that there are drawbacks in this particular case. So the third way is polarizer triplets. Most of us are used now to measurement of linear polarization with a triplet of polarizers 60 degrees apart. It's the most common way that people use. It was pioneered back in the early 20th century. There's a guy named Ullman from Sweden who measured an eclipse using a tri-camera system during World War II. And so he didn't get recognized as much as one might expect. Do your dissertation during a world war. It's challenging in many ways. But it's a pretty straightforward way. Lots of people have written codes to do inversions of these. I like representing polarization with triplets. The reason is it's symmetric. You have 3 intensities, right? They're all exactly the same. They're all non-negative, so we can use it for punch. And you can easily interconvert between different polarizer systems. So you can have a set of 3 physical polarizers to measure, but the equations work backward too. If you have a set of Stokes vectors, you can convert to a virtual polarizer triplet, essentially predicting what the brightness would be through 3 polarizers at a particular set of angles. That means you can represent, not only can you measure polarization this way, but you can represent it this way as well. And that representation is very useful for what we need for punch. So that's how we represent polarization in the punch sock, in the data pipeline. Drawback, maybe it's a minor drawback. This is not as familiar to most people as the Stokes vectors, right? If I give you a polarizer triplet, you're likely to say, what do I do with this, right? This composed to as opposed to a Stokes vector. Let's take a little side trip here. So pause. We've looked at 3 systems of describing linear polarization. I'm going to go into a different system, which is a similar 3-space, and outline how we describe color. And at the end, I'm going to show you that, in fact, the way we describe polarization is exactly analogous. So with color, you've got red, green, and blue. The screen you're looking at has red, green, and blue phosphors, right? And they represent color by illuminating each pixel with some value in that 3 space. And, all right, and there's some weirdnesses. You can't produce all the human perceivable colors with any particular triplet of primaries. You can using this international XYZ standard, which is really interesting. In 1931, the international, I forget what it stands for, something de éclairage, it's in French, but CIE is the name of the committee. They defined these 3 primary colors that allow you to represent any visible color. They did it by sweeping the negative spectral values under the rug, right? The pigments in your eye they're not mutually orthogonal. There is no color that excites one pigment and not the other 2, right? So you can't represent all the colors you can see without having negative intensities, which aren't possible. So what they did is produce these primary colors that have negative going spectra, and then you can represent any color using those. So that's this XYZ system. That's kind of neat. There's another system which, if you're an artist, you've used, right, which is HSL, hue, saturation, and lightness. So lightness is sort of the equivalent of yours, how bright things are. Hue is the color wheel that we all studied in grade school, and saturation is either a relative value, intensity divided by something called chrominance, so it forms a conical coordinate system in this RGB cube, or you can instead describe chroma and make it a cylindrical system. So you've got this L is your lightness, right? Equal amounts of RG and B. Tells you how bright a particular color is. Hue is a planar angle in the plane perpendicular to lightness in the same 3 space. And then saturation is either a cylindrical or a conical radial coordinate. So when you look at HSL values, you'll look at them completely differently now, right? They're just coordinate transformation out of RGB space. And this is all sort of based on, it's really interesting to read about these processes because people have fought over them for years. And it turns out, of course, they're mathematically related. The way your monitor, as you're logged in, describes color is different than how the screen is producing it. We use something called YCBCR, which has a Y is basically the same thing. It's the lightness signal, equal amounts of red, green, blue. And then there are 2 chrominance signals, which describe directions in the perpendicular plane, the chroma plane. And so CR tells you the amount of red, and CB tells you the amount of blue. And it's just another way of describing this RGB combination. You can see this is an orthogonal coordinate system that just happens to be at an angle to the RGB system. This turns out to be how your eye represents color. And there's some experiments you can do, which I won't go into here. If you Google chimerical colors or Stygian blue, you can actually do little biological experiments on your own eye and see colors you've never seen before. It's really neat. But that is the way we perceive color. We have a yellow versus blue opponent system and a red versus green opponent system. So we have 1 unsigned value and 2 signed values. Should look familiar now. So it turns out those are exactly the same as the 3 polarization systems I just showed you. We have RGB, we have hue, saturation, and lightness, we have YCBCR. These are 3 different ways to represent the same color space. And if we just apply this analogy, if we substitute these values, IM, IZ, and IP for RGB, we get that tripolarizer system. And it has exactly the same mathematical relation to the other 2 as the color systems do. If we substitute in our beta is half the hue angle, our relative polarization is saturation, and our intensity is the same as lightness, we get out that grade school I beta P system. And of course, YCBCR turns out to be the Stokes coordinate system. So anytime you think of a linear polarization state of light, really it's mathematically exactly the same as a color. This is one reason why tripolarizer systems are so nice, because they're exactly analogous to RGB systems that we're all familiar with. So anyway, I'll pause here for a minute because that was a lot of coordinate systems all at once. And then we'll do a little coda on noise. Yeah.
It's another advantage of three equal or balanced coordinates, being that if you do an inversion,
Mm-hmm.
you're not having one that you're super sensitive and two that you're less sensitive to. You've got an equal. So when you do an inversion matrix, you've got equal balance between your equal sensitivity to those.
I think you've nailed it. Yes. When you represent things symmetrically,
Right.
then noise and other effects propagate through the system exactly the same in all three. Right. So exactly as you say, you're sort of equally sensitive to perturbations in any one of those.
It's remarkable. This is, I would say, just about every science system you work in, where you've got data, you've got a model, a bunch of physical parameters you want to derive from the data. You have to do an inversion where you basically match, and you're doing a fitting algorithm where you match one to the other, and you've got exactly the same problem, whether you're doing spectroscopy of the sky, or whether you're in situ measurements of plasmas, or inverting all sorts of anything in the chemistry in the lab. I'll bet that this is pervasive throughout. It's sort of standard geovisible inverse theory.
Yeah, that's right.
Right.
The reason I wanted to give this particular talk at this particular place is I think we all lose sight of how simple this is in our analysis, right? We learn the equations, we track them through analytically, but I at least never sort of got this deep intuition until I really dove in this way, right? Through the visualization.
Mike.
Oh, go ahead, Mike.
Craig, sorry, I'm not an expert in these kinds of things, but this is a fascinating discussion of the things. I hadn't really realized the interplay of these color systems. I'm just curious if there's a way to use everybody's least favorite color table, the rainbow, the RGB color table, to actually display the full 3D, vector information there and get something out of this. Dave Heisel's done some stuff with radar data that is in this space that I have to admit to not fully understanding, but maybe that's where you want to go with this, and I'm off the base there.
We are not going there with punch, but it is a direction to go, and you're exactly right. Now, the magnetograph community already use a color wheel to represent direction, and I don't know whether David Elmore or Steve Tomczyk sort of started using the color wheel because of this insight, or whether it was a coincidence. But yes, the color wheel is a very natural way to represent direction because of that. Yeah.
Thanks.
Thank you. All right, just so I can get you out of here at the top of the hour, we're going to move forward. So there is one other thing. We have to talk about kinds of PB. And this is an unpleasant topic because this is a case where we as a community have done a shite job of producing a uniform data product across the decades. We have, here's the polarization space at a particular pixel, right? That's the YCBCR, or the Stokes system, right? And so we got our tripolarizer RGB system, and when we got our Stokes I, Q, and U. And of course, we can rotate those Q and U to get the perp PB. And you'll notice I've been putting a perp on the front of the PB. This is why. With punch, we treat PB as a quasi-Stokes parameter. It's been rotated to match the particular pixel that it's measured in. And of course, there's a PB prime as well that's 45 degrees to that. And so in this funny polarization coordinate system, it's 90 degrees. But in real space, it's 45. It turns out there's another way to measure polarized brightness, which is to measure total polarization, regardless of angle. Now, PERP PB is the main PB product used by the ground-based community, right? This goes back to Leo, Altshuler, and Perry. The various HAO coronagraphs have been designed to take advantage of this BT minus BR, right? I mean, the Mark II, for example, had a linear detector that scanned radially, and so it physically mapped out this BT minus BR. In the space community, ever since Monroe and Jackson, everyone's been using this angle-independent PB, which is just fine. And it turns out that because the corona is tangentially polarized, you get the same answer in the absence of noise. And so you might as well use circular PB because then you don't have to deal with the angle. It's very convenient. But now that we actually care about making real measurements, we have to think about noise. So let's talk about noise. If you make a tripolarizer measurement, as in that inset, you find that there's a point somewhere in that 3 space, which isn't rendered up there, but it is rendered in the larger frame that we'll get to in a moment. So there's a point in here somewhere, and that corresponds to 3 brightness values through your 3 sensors. But each of those has noise on it. And so the point is actually the measured value that you get is going to be part of a cloud of points that form an ellipsoid around the real point in 3 space. Okay. So now let's project into the polarization plane over here on the right. So this is, in color space, this would be the chroma plane, but because it's a polarizer, it's the polarization plane. These green isolines are isolines of circular PB. The blue lines are isolines of PERP PB, which is the Quasi-Stokes parameter. Here's the projection of our ellipsoid of noise, which forms an ellipse in this plane. And what I want you to see is when we project down to another, one more dimension down into a data product, the PERP PB and the CIRC PB are tangent at our measured point, right? That reflects the fact that the corona is tangentially polarized. So CIRC PB and PERP PB give you the same answer, okay? But the noise around there is that cloud is bisected by the iso line of PERP PB. So you're just as likely to go up as down from the influence of noise. And if you average a bunch of those data together, it will have a 0 mean and you'll converge to the actual value. That is not the case for circular PB, right? You can see that right there. That circle does not bisect that noise ellipsoid. And so there's a net mean value to the noise. So if you take a bunch of PB images that are noisy and you average them together, or if you take a PB image from your coronagraph and you average together pixels, you smooth the pixels in that data product, you will not converge to the true PB value. You will converge to something larger. There's a systematic offset. And so if, as the ground-based community has done, you adopt this quasi-Stokes version of PB, you get one answer. If you adopt, as the space community has done, this circular direction-independent version, you get a different answer. And this is something that is sort of basic. We can all keep track of it if we know to look. But the definition of PB has been so blurred over the years that there are papers in the literature, I'm not going to name any names, but there are papers in the literature where people have compared data products from ground-based coronagraphs and space-based coronagraphs with different data products being produced and found that they didn't agree. And this is why they didn't agree, because there were different data products. This particular insight is not mine. It came from Bert Inhester, who published a really neat paper on this last year. And of course, this is the kind of thing that at one time everyone would have just taken for granted, I guess, but it was taken for granted so long that it was sort of lost from the collective consciousness. So anyway, watch your data products. If they're non-linearly related to the source data, you will have these weird noise effects that you have to take account of. Also, you should define what kind of PB you're using. So conclusions. we've been over a lot of ground. Punch is on track and exciting. I'm very excited about it. You should be too. PSF correction works, and it works well. In those sample frames that I showed you, we understand the artifacts that remain, and we'll work to avoid them mostly by reducing noise in future measurements. Linear polarimetry, we use this tripolarizer system that people have used for measurement, but that we also are now using to represent polarization as well. We use PERC-PB, as all good people should. And you should take away this insight that relates polarization to color states. That's it. Thank you.
Okay, so it's open for question. You just unmute yourself and ask the question, or raise your hand, whatever.
Oh, Joan's got her hand.
2 hands, 3 hands. Two hands.
Joan, go ahead.
Oh yeah, very nice talk. So we do a coordinate transformation with K-core to basically get us into the tangential frame. We're not doing, q squared plus u squared or.
Right.
However, what we cannot avoid, of course, is averaging first at the camera to get sufficient number of photons to get an image. One thing I'm concerned about as I'm watching your talk, we do this coordinate transformation that I constructed after we do distortion. So we do a demodulation matrix, and then we do a distortion correction, which is nonlinear. And I'm trying to think if that is going to screw us up a little bit. In essence, we are still going into a perpendicular coordinate system, because we also have to remove sky polarization, not just instrument. So we have to, that was the cleanest way for us to do that. So I need to think about that. You have a lot in here. So I need to get down to those details of if we've done the distortion first, will that introduce a little bit of noise because it's a nonlinear process.
Joan, I get the feeling that you and I have the opportunity to spend some quality time in a room together in front of a whiteboard.
Yeah, okay. Sounds good. Sorry, I'm not there.
Soon.
Okay, thank you. That was
Thank
good.
you.
Nice.
Were there some other hands up I didn't see?
Other questions?
Maybe they were claps.
Maybe. All right. Well, Joan, I will reach out to you. We should definitely have that time in front of a whiteboard.
Thank you. That sounds good.
So you're wanting to get basically electron density, assuming that this PV comes from electron directly proportional to electron density along a line of sight, integrated along the line of sight,
Yes.
because that's what you measure. But what are you looking for? That gives you your image of your line of sight integration of electron density. But what is your, do you want to then convert that to in situ, model that and get local densities of a three-dimensional structure, observe it over time and have its motion moving through? What is the follow-on product?
So depending on the science objective, we do different things to those data. So for example, one of our science questions is, how do CMEs evolve and move in free space after they're ejected? Do CMEs get deflected? Right? Does the interior evolve in a significant way, or is it really just preserving what was in the corona at the time? These are sort of unknown, outstanding questions. And so those elements are really about tracking the morphology of a bright bang in 3 dimensions. There are other questions like how does turbulence form, where we really care about the density in a particular blob. One of the follow-on products we have is we have two different teams making tomographic maps of the solar system in electron density. The team from UCSD, or the UCSD Convergence, and there's a team at Aberystwyth led by Hugh Morgan that's also doing that. So we have two different pathways. But the idea is we ought to be able to use kinematics to constrain the shape of the data, right? And use that to get a tomographic version of the entire solar system. So there we'll be trying to track how individual boluses of electrons move through the entire solar system all at once. I hope that answers the question.
Yeah, no, I'm just thinking in terms of you're at the stage of building an instrument that's going to make these measurements, and then you need to do a whole bunch of stuff to get out the visible quantity that you really want. And it's interesting. I'm very impressed that you're this far ahead. Last week, I'm on the science steering board for the Clipper, Europa Clipper mission, which is going to go launch in 2 or 3 years. I'm looking at the timing there. They've got a long way to go before they get the data. They don't immediately get into it. But the teams haven't even begun to think about how do I go from what counts or whatever measurement you have in your detector and converting that into physical, meaningful quantities, a density, a temperature, a flow, or whatever it is. And I'm thinking about encouraging teams to sort of get ahead about being ready. And I was very impressed with your idea of the SOC being up and ready on day one. And this is it's very hard when the hardware guys, I say guys, hardware people, usually guys, are wanting funds and hogging the funds because they're going to overrun. They always overrun. I don't think hardware's ever underrun. And, they pull away from the science. And so the people who were doing the prep work for the science tools, they have to skimp and save and wait. So I encourage you as PI to, as I think you are, stomp the table and say we need money for the science. Yeah, I see Sarah's responding to all of my comments. But yeah.
Thank you.
Good. I'm impressed. I'm punched.
Kevin has raised hand.
Kevin.
Hey, hi, Craig. So you described with the 3 60-degree measurements. What happens if you do something silly like do 3 45-degree measurements instead?
I will refer you to our 2022 paper, which covers exactly that.
Mm-hmm.
Basically, as long as you can represent the system with any set of polarizers that aren't all multiples of 90 degrees apart,
Mm-hmm.
right? As long as you're linearly independent in this this funny 3 space, you can back out the polarization state from any number. But of course, 3 is the ideal number, because then you have a symmetric system.
Okay, I'll take a look at it. Thanks.
Cool.
Are there any other questions?
Can you show Sarah's comments in the chat?
Yes. Yeah, in person people don't see it. So Sarah's first comment is come to our summer meeting, friend. Second comment is we will talk about all the amazing various science we will be able to do with punch data. And the third comment is the SOC is going to be providing us synthetic noised punch data products for us to test our science analysis techniques and compare to ground truth.
Yeah, right. Yeah.
Thank you, Sarah.
Indeed.
Well, all right. Thanks, everybody, for your time and attention. Glad to have you here.
Thank you, Greg. So let's thank our speaker again.
Right. Yeah, there's the claps going. I haven't seen that going up through the before.
That's awesome. Fun. we still recording?
I'm about to turn it off. I think we're done. Thank you, Craig.
Thank you.
Thanks, really interesting.
Thanks. Come on.